All right, so today what we're going to be talking about is it's called Snell's law or Snell-Descartes law. Really, it should, another the most obvious phrase for it is it's the law of refraction. So just kind of go through refraction once again. So we're talking about light with this. So if I have up here, so if I have air up here, and that blue line represents the surface of water. And so we have water down there. If I was looking at light, so this light ray, so let's say this light ray is coming in at an angle, and it's going to cross from, so it's moving at a certain angle in the air. And the way that they measure that angle, it's not kind of this angle here from kind of your base up to that. So what they do is they consider there to be kind of a 90 degree, that would be like a normal there. So they consider that. So the angle that they're really concerned with is this angle right here. And so this is what they're going to call the incidence angle. It's the, I could probably write that a little bit better. So this angle here is the angle of incidence. It's the angle that the light's moving in kind of the first medium, the first substance we're talking about. So in this case for us, it's water. Sorry, it's air. I'll get that right eventually. So we have our light moving through air, and then after it, hits the surface of the water, it's going to bend a certain amount. Because if you remember from refraction, it's the bending of a wave as it goes from one medium to another, but it's really that bending is being caused by a change in speed. So let me draw a new angle here. Okay, so we can see kind of how it was coming in at kind of a sharp angle, and then it kind of flattened out a little bit. And just like with our angle of incidence here, how it was measured from that normal, really this angle here, the angle of refraction, the refracted angle, and these two things are going to be different. So really the way that we kind of talk about it is, so the equation we're going to use for the most part is, traditionally it's been called N1, or the index of refraction of substance 1, times the sine of angle 1, or the angle that the wave is moving in substance 1, is equal to the index of refraction for substance 2 or medium 2 times the sine of the angles moving in substance 2. Really, we're going to rewrite this though, just make it a little bit easier. We're going to have the incidence medium, so where it's starting in, times the sine of the incidence angle equals the refracted substance. So what did that wave, what did that ray of light move into, times the sine of the refracted angle. These two things are the same way. I just think using I and R just makes it a little bit easier to understand than 1 and 2. So using a new phrase there, the index of refraction. Typically the way that they find what the index of refraction really boils down to, it's the speed of light in a vacuum divided by the speed of light in the medium. That's really what's going to determine the index of refraction for a certain substance. And if I want to write that shorthand, I would go like, so C is the speed of light, or sorry, alright, so equal to the speed of light in a vacuum over the speed of light in a certain medium. So we know that certain substances are going to slow down the speed of light to some effect, and really we're talking about the net speed of light, but hold on to that for later on. So really what we're going to see is the slower that light goes in a medium, the bigger our index of refraction is. If the two speeds are the same, you would get an index of refraction of 1. And really what that means is we're not going to get the light to bend at all. Because if our n is 1, that means these two angles are the same thing. But the more the light slows down, the bigger n gets, the bigger of a difference in angles we're going to see. So kind of how this works. So once again, we're kind of using this one right here. So I have my two substances here. So if I'm just going to go through how the equation kind of works, in a practical sense. So I have air and I have water. So really what I would need to know is I need to know the angles that the light is moving in, if you will, in the air, and the angle it's moving at in the water. So down here in question 2, so let's just jump into the practice problem. Find the angle of refraction. Okay, so let's even start writing down what I know. What's the angle of refraction? So that's what I'm looking for a ray of light that enters a bucket of water, okay, water, from air. All right, so I did my diagram, at least at this part, right, at an angle of 25 degrees to the normal. All right, so that means since it's starting in the air, our incidence angle is 25 degrees. So I know the incidence angle is 25 degrees. So then the other things I need to know is what is the index of refraction of my incidence material, which in this case it started in the air, and then what is my index of refraction for the refracted medium, which in this case is water. And to find those, we're just going to go to a chart. So down here, I have a list of the different indexes of refraction, or indices of refraction, I should say. And they go through different substances. So we up here, we have solids here, liquids here, and then gases down here. And one of the big things we should be taking away from this is that the solids, have some of the highest indices of refraction, like cubic zirconia, diamond, zircon, and then the liquids, they're, from here we can say they range from about 1.3 up to about 1.6. And the gases down here, their indices of refraction are super, super small. Like they're almost 1. A lot of times if you find practice problems online, they're just going to say that the index of refraction for any gas is 1. Air, I've seen it be 1.000293, as it is here. I've also seen it be 1.00033. So there's a little bit of wiggle room with this. So we'll just use the one that's there. If you want to get really, really, exact, use the whole thing. Otherwise, you could just use 1 if we're talking about air, carbon dioxide. All right, so let's go ahead, bring that back down there. All right, so first thing we need to do is find the index of refraction for our incidence material, or starting material. And then the ray of light is starting in air. And once again, we could go through and write 1.000293. I think I might just to practice with it a little bit. 1.000293. All right, and then we need the index of refraction for our second medium, the refracted medium, and that was water. Let's see how well I can. Nope, too far. There we go. So water's right here. It has an index of refraction of 1.33, if I could do that right, 3. All right. So right now, I have everything I need to do to set up this problem. So let's go back through, use this. So with Ni is 1.000293. That's being times the sine of the angle of our incidence angle, so that would be 25 degrees. It's equal to the refracted index, or the index of refraction for the second medium, 1.33 times the sine of the refracted angle. Okay, and that's what the question's even asking for. So now the first thing I'm going to do algebraically, if I'm going to get that sine of refracted angle by itself, divide both sides by 1.33. So that cancels out here, moves it over there. But now, if I'm going to go from the sine of theta to just the angle to theta itself, I need to essentially take the inverse sine of everything over here. All over 1.33. So this is where, for some people that are really, really good at keeping their order of operations straight, go ahead and kind of type it in this way. Me personally, since it's been documented, I have some pretty major calculator issues, especially with the one that comes with this operating system. I'm actually going to use a different calculator, and I'm going to figure out I'm going to calculate this part first before I go through and do the inverse sine of it. All right, so we're going to go to the sine of 25 times 1.000293, and we're going to divide that by 1.33. All right, so for that part, what I got was, when I calculated all of that together, I got 0.3178. 5 sounds good. So I just need to take the inverse sine of that number there. Okay, and it was 0.31785. All right, made sure my calculator was in degrees there, and what I got for that when I took the inverse sine of that number, I got an angle of 18.5 degrees. All right, so coming back up here, the angle of refraction down here we found to be 18.5 degrees. So we had a change of 6.5 degrees, so that's pretty substantial from light going from the air into the water. It bent quite a bit. And once again, the big classic example of where this is useful tends to be in like bow fishing, using a bow and arrow to fish. This shows you that you actually should aim. Let's see if I can get this right. You aim above where you see the fish, I think is how that works. And really, we could go through and use the index of refraction stuff here to figure out what the difference in the speed of light is. There's a lot of different things we could do with it. But yeah, so that's typically Snell's law and kind of how it's used. This tends to be used a lot for designing contact lenses, eyeglasses, the materials you can use for it. And then in microscopy, this becomes important because there's times where we don't want the light to refract at all. That would be like with an oil immersion lens to view very, very small, like bacteria, stuff like that. All right, I think I've talked long enough. That's Snell's law. That's kind of how it works. That's the math. That's kind of what's happening with the light. Good luck with practice.